you two to start with problem 2.
These students are working on a set of problems which model real-world situations. They are using linear programming and are already familiar with solving by the graphical method. The teacher is interested to learn how problems like these can promote discussion and through this develop understanding about the practical limitations of the graphical approach.
We need one which shows the x terms and then one which shows the y terms, don't we?
So each of the 3 problems was designed to draw on one possible complication that might exist when taking a purely theoretical mathematical solution to one of these problems and applying it to real life.
So it's that point there. So it's like 32 and 11.
What's it supposed to equal?
Meant to be less than or equal to 300. 186 plus like 296. I think that's like the closest you can get without it being like half a table.
What have we got?
We think it's 10 tables and 32 chairs.
Do you think that there might be any potential issue with that problem?
You might have not enough chairs for the tables.
Because how many chairs are we looking at per table at the moment?
3.2.
Yeah.
So is there perhaps any other adjustments maybe to perhaps improve the problem?
Maybe you need to have a ratio of 6 to 1 or I don't know.
So maybe think about a minimum number of chairs per table.
Yeah.
12.5, 7.5. See, that's the x value, that's the y.
So what's the solution to the problem? How many badges should they make every day?
Well, we can't have half numbers,
Right.
so we're going to have to take that to the whole integer.
Okay, have a think about how you might get around that.
Is that right? Is it
1020.
Is it 1020?
Yeah, they're both, there's parallels.
Yeah.
If students are working through them, doing every single step, including the graph drawing, one of these problems alone might be 30 minutes and they would get a lot from that, but by having time to look at all 3 meant that we could look at a range of issues and they had time to make mistakes, learn from those mistakes and come up with a final solution that worked.
That's 8.5. Yeah, just the 722 one.
Okay, 722, and that's the same profit?
Yeah.
Yeah.
How many of each side should or she could make either? The bloomer uses less flowers.
Right, so we're back onto integer solutions now. So is it going to be 712 then? That's going to be the furthest across.
Can you not have an 812?
No, 812 falls in the green, so that's not feasible. The actual answer is they need to make 12 badgers and 7 ducks per day. Cool. On to the next one.
Here we were able to explore 3 questions in the lesson and within the 20 minutes or so that I gave them, most of them had go at 2 of those problems, meant that they could then contribute to the whole class situation at the end. We'll start with problem 1 and we ended up with an issue. Can you tell us what the issue was?
So when we dragged the profit line over to the intersection of the other constraint lines, the coordinate was 12.5, 7.5. You can't have non-integer solutions to a problem like that. So we needed to find the highest profit of an integer answer instead.
How might we adapt our solution?
Could they do it over 2 days? So just double everything.
Okay.
And then you've got 25 and 15.
So problem number 2, I think when you got your original solution, you felt that there was something that we had to address there.
There wouldn't be enough chairs to go around each of the tables.
So
Right.
you had to take in the real life application of things. It's
Okay.
not just theoretical.
How can we modify the problem to address that?
You'd have to form an inequality combining x and y to allow for how many chairs you wanted around any one table.
Right, okay, so we'd maybe add in an extra constraint. Problem number 3,
Both solutions give the same maximum profit.
because it's parallel, isn't it? It's leaving this feasible region. If we just focus on the integers, there's 2 different values that will give us the same profit. What other factors might be taken into account if you were the florist deciding which of these options to go for?
I could say which one sells better, which one's more popular with the customers.
Ultimately, this is what discrete maths is doing. We are modelling real life situations, so sometimes we do need to adjust our answer and think about other factors that might come into play.
They got very engaged in conversation about which solution was better, where there were two solutions, and why an integer solution might not always be preferable to the solution with the 0.5s in.
It often is those final little ends of questions where they have to think a little bit beyond the mathematics and come up with a contextual answer that makes sense. The fact they had time in this lesson to bounce those ideas off one another hopefully means that they've got more strategies for dealing with those questions themselves when they're in that exam situation.
I like it brings to the fore that decision maths informs the decision, doesn't necessarily make the decision for them.
Yeah, it's a nice way of putting it.
Mm.